Okay, so states of matter. Now, the funny thing is, there are multiple states of matter, and we've actually done most of them earlier. We've discussed solids in bonding when you had macromolecules, metallic lattice, ionic lattice. And intermolecular forces are already discussed. What really is left to talk about is the mathematical relationship of multiple factors of gas. What we're really doing, and more correctly called from this is, we're looking at gas laws, really, and behavior of gases. That's specifically what we're doing right now. We've already done the other two states, and the intermolecular forces and everything else, which is also states of matter. Now, we're really looking at gas laws. And to understand ये हम कर क्यों रहे हैं, it makes sense to understand why we had to study gases separately. There was a need to understand how gases behave in terms of how much work they do, energy they produce. If I compress them, I expand them. There was the rise of the steam engine. The steam trail engine was a massive revolution in the Industrial Revolution, because then you could use, because there was no cars, so how do you move material? Put them on a train, and at that time you just heat and use the steam to drive pistons and drive trains. So there's a lot of gas expansion on heating. So we wanted to study, can we predict, because if you can predict, we can make the right kind of train engines and all that stuff. So we wanted to predict how expanding gases affects pressure, which then does work. So by the way, this kind of stuff will also come in physics next year, in thermodynamics, because they are more interested in how this can be done. Our job is to understand the basics of the math for this, and then also talk about how the assumption that all gases behave the same way is not exactly true. That we'll discuss tomorrow. Today, we'll discuss that assuming all gases behave the same, there's certain things that we have assumed for gases. Most of them have become true now. ज़्यादातर ये laws पहले बने थे to explain gaseous behavior. And now that it's called the theory of gases, because most of it is explained theory, but a couple of parts are assumptions on our part. And the reason why we have assumption is because if we were to correct, because we know that steam and hydrogen don't behave the same way, because hydrogen only has van der Waals due to induced dipoles, while steam has hydrogen bonding. Their properties differ because of this. But most times at the normal conditions of the earth, that differences only don't even account for less than 0.1% or 0.02% of difference. That's 10,000th of a difference. The difference is being so small at the most macro scale of human beings in this temperature that we do not care then. We assume that they're all true because we just want an approximation anyways. So the need at that time was solved by approximation also. Assuming steam and ammonia and hydrogen and oxygen all behave the same way. But we already know how gases behave. Now, this was first determined when we didn't know about molecules. Now we know atoms and molecules exist. This theory was made not knowing, not having proof that they exist. But we figured that gases must be made of molecules that are moving randomly. Now we know they do. And the second thing we know is that there's energy comes from the temperature. If you increase the temperature of a gas, the molecules will move faster, which means their speed will increase, which means their average kinetic energy will increase. So theoretically, the definition of temperature or absolute temperature is that it is a measure of the average kinetic energy of the molecules. Average because not all the molecules have the same energy in this room. So it's an average energy. Okay? That's a basic assumption, that the molecules in this room are not the same energy, and we know they're not. But if I were to turn the AC off right now, all the molecules in this room will start moving faster because heat will increase their kinetic energy. Then this assumption is there that since you take physics, or at least most of you do, that you might have heard of momentum, and momentum collisions can be elastic or inelastic. And we are assuming that collisions between all molecules here are perfectly elastic. No loss in kinetic energy. Then another idea that comes in count and is that we discussed it using partial pressure was that we realized that the pressure that a gas gives comes from its collision between the molecules of that gas and the walls of the container. That's how we know pressure is generated. That's part of kinetic theory. These are all the things we know of. Now, knowing and then assuming some things. Now, to solve for the math for this, we assume the next thing. So these are the theory points, the ones on slide number 1 for you, all 4 points. Now, 5 and 6 are really the assumptions. And those assumptions are based on 2 things. Because उनकी जो assumptions करने से ना मुझे इतना मैथ में फर्क नहीं पड़ा था. Assumption क्या थी? पहली बात है कि we assumed, the last part here, that there are no attractive forces between molecules. Now, having attractive forces makes a difference, and we'll discuss that difference tomorrow. But today, let's assume no gases have attractive forces. That means no molecule is pulling other molecules. Second is that the volume of molecules is negligible compared to the volume of gas. Now, why does this assumption even exist? It might help you to remember कि मैंने example दिया था 1 mole of water का, which is in the volume in a liquid state, it is going to be 18 cm3 because 1 mole of water is 18 grams. 18 grams is 18 cm3. But if I were to vaporize that 1 mole of water into steam, assuming at RTP, which I cannot do, but let's say we could do that, 1 mole of gas कितना volume occupy करता है? 24 dm cube, right? Or 24,000 cm cube. ये जो volume आया था, ये आया था volume of molecules packed together. और ये volume expand क्यों हुआ? It's not like molecule बड़ा हुआ था. The reason why the volume expand was now the molecules are so far apart that the space they occupy will be 24,000 cm cube. Which means the difference in the volume, liquid or gaseous state, the difference is all the empty space. Meaning 23,982 is just empty space. Which means that molecule छोटा होगा और molecules के बीच में distances बहुत ज़्यादा होंगे. And if that's the case, what we do is, because you know the empty space in this case would be this minus this, 3,982. What this statement is saying is that we are assuming that this is so small that this is really this. Because this is so small. So meaning that in a gas container, if this is my container and those are my molecules, I will assume that they have zero volume. And the reason why this assumption is important is जब भी आपने O levels में पढ़ा होगा, Boyle's law पढ़ा है ना आप लोगों ने. And Boyle's law talks about compressing and expanding gases. When that happens, they're not compressing and expanding molecules. They're only compressing and expanding the space. And so the math becomes harder if I don't do this. It's not impossible, but it becomes harder if I do not ignore the volume of molecules. Harder and longer, but not much more accurate. Because the accuracy will only affect the 5th significant figure. And in the real world, 3 to 4 is enough for us to even live the world. That's why your syllabus says correct to 3 significant figures. Because for us, that is enough accuracy in everyday life to live by. We don't need to be more accurate than that to run a life. So at the macro level, we assume that the volume of molecules is negligible compared to the volume of gas. Which means, why? Because zero distance, this distance is thousands times larger than the size of the molecule. अभी तो फिर भी बड़ा molecule का size है. The real world में, like if I move my hand like this, it's very improbable that I even hit 2 molecules. Because mostly it is empty space. That's why I can do this. That's why I can't do the same speed in water or solids. Because there are molecules there. Here there's hardly any molecule. If the gases were as packed as liquids, we could not move around. We can only move around because it's mainly just empty space. Okay, so now to end this chapter, I'll just do a couple of basic laws to start off, because I want to give you a couple of questions to solve at home. Okay, one of them is Boyle's law. You definitely have heard of this in physics, yeah, and even there's Boyle's law, and then there is Charles' law. Okay, so this Boyle's law is something that you've seen in physics before in O levels, I'm assuming. And this relationship that we were going to talk about yesterday, we'll continue, is the fact that this talks about how the pressure and volume of a gas vary. And the idea is that the pressure volume of a gas is inversely proportional to the pressure that the gas exerts, if the number of moles of gas and the temperature of the gas are held constant. What that means is that pressure is inversely proportional to the volume of the vessel containing the gas. Because the reason why we say volume of vessel is because the gas takes the volume of the vessel it's in. So the pressure the gas exerts on the walls of the vessel is inversely proportional to the volume of the vessel. If you rearrange this, you get P equals to K over V, and if you take the V on the left hand side, you get PV equals to constant. And this is a very important relationship for our discussion for today, that P into V of a gas is always going to be a constant if the number of moles and temperature remain constant. And this leads into the formula P1 V1 equals to P2 V2. This is something that you've been using in physics before, right? So the idea simply means that if you double the pressure from the existing pressure, the volume should half, double half. That's how it will work. I mean, if I'm comparing it. So if I start with, let's say, 280 m and 5 dm cube, and if I increase the volume to, let's say, 10 dm cube, what's the new pressure? That would be 180 m. And you work that out, it's pretty simple. On its own, it's nothing great, but we will be using this in conjunction with other laws that we'll see. इस relationship का ना हमें graphical representation भी चाहिए. One of them is drawn for you. Since pressure is proportional to 1 over volume, which is also the same thing as saying 1 over pressure is proportional to volume. And so volume against 1 over P or 1 over V against pressure is going to be a straight line passing through the origin. So I'm going to sketch for you 4 or 5 relationships graphically on the right, on this side, so that you can remember and learn how to draw them also. The first one is simple, pressure against volume. That is an inversely proportional relationship like this, which is why pressure against 1 over V is a straight line passing through the origin. And pressure against PV, knowing that PV is a constant, what that means is whatever pressure is increased, the value for PV stays constant horizontally. This is a constant. So P against V is inversely proportional. P against 1 over V is directly proportional. PV against P is a horizontal line. And these are some of the ways that we can represent Boyle's law. All of these 3 cases, we are assuming that temperature and the number of moles are constant. Because if they change, the relationship will change. So scrolling back now to to a particular skill check here. Of all the 4 graphs, which would represent the graph of volume against pressure for a fixed mass at constant temperature? D. Yup. Absolutely. Then, now, the next law that we come across is called Charles' law. And this is the relationship between the temperature, the absolute temperature of a gas, and the volume the gas occupies. The absolute temperature of a gas and the volume of the gas occupies. And the relationship is that the volume of gas is directly proportional to the absolute temperature, if pressure and moles are kept constant. So what this results in is V equals to KT, or V over T being a constant. This means if you double temperature, you'll have to double volume of a gas if the pressure remains constant. It's this kind of relationship. If you increase temperature, the gases have to move, they're moving faster, so you have to occupy more volume for the same pressure. The relationship is volume against temperature is a straight line, because this is the directly proportional graph. So PV was not directly proportional, but this one is. This is the second law. We'll put them all together, this one and the next one also. And the next one is, this is the one that you've been using, from which you've derived the idea that 1 mole of any gas at RTP occupies how much? 24 dm cube. That is derived from this relationship, which is that at equal pressure and temperature, which is room temperature and pressure, you guys use a very specific temperature and pressure, but for any temperature and pressure, equal volumes of ideal gases contain the same number of moles. This is what you guys remember, that no matter what gas you have, if there are two gases having the equal volume, they must have equal moles. And extraction from that was that, therefore, the volume a gas occupies is proportional to the number of moles it has, which means that V equals to Kn, or V over N is a constant. So now, you guys have just witnessed Boyle's law, which is a relationship between pressure and volume, Charles' law between temperature and volume, and Avogadro's law between volume and number of moles. Now imagine you did this, that this is the mathematically correct way of doing it, but obviously not theoretically correct way, what I'm showing you right now. That the idea was that P1 into V is a constant, let's call it K1, V over T was a constant, and V over N is a constant. These are the three laws we saw, all three having volumes of gas. And if I combine them into one relationship, PV on the numerator and NT on the denominator, and what I know is that this into this is a constant, and V over N is a constant, and V over T is a constant. So mathematically this relationship is also a constant. Let's call that K4. But that constant actually is now called R. It's known as the universal gas constant. And what that does is, it mathematically connects Boyle's law, Charles' law, and Avogadro's law into one equation. And we call that equation ideal gas equation. And the letters are only rearranged to make them into alphabetical order. But you take this on this side, you get this relationship. And the beauty is, you already seen PV in another relationship. In what? In P into V as a unit, as a combined term in Boyle's law. In Boyle's law, P into V was a constant for any gas. And here PV equals to nRT. That means if this side is constant, if temperature and moles remain constant, which is why this side is also a constant. So I've got that relationship now. Boyle's law in terms of mathematics, because I made PV the subject. And this is called the ideal gas equation. Now, all the derivation I've done, all just implies that this equation represents in its form Charles' law, Boyle's law, Avogadro's law, all the laws. And you can use one equation to solve all questions regarding gases. And iske saath, it's always good to remember that there was another relationship between number of moles and mass. Number of moles of anything is the mass over MR. So using these two relationships, we can solve any question. Any question. Okay? Now, look at the question in skill check number 3 given. This is what we... sorry, I should mention this. This is the ideal gas equation. This equation, everything is in SI units. So instead of, not MR, but what is in this equation? In this equation, में Pascal's a volume hai, nRT hai. Pascal's is the pressure of gas. They'll ask you sometimes what is P. Pressure of gas measured in, either you can say Newton per meter square, or this unit is also the same as Pascal's. Pascal's is Newton per meter square. Volume will always be in meter cube, which means if they give you cm cube, remember that 1 meter cube has 10 to the power of 6 cm cube. And the reason for that is 1 meter cube is 1 meter cube like this, and 1 meter is 100 centimeters. So 1 meter cube is 100 centimeters cube. When you do that, you get 10 to the power of 6 centimeter cube. So if you're given centimeter cube, you're going to have to convert that into meter cube. Because in this equation, we're going to use SI units. This equation actually will also be used next year in physics, in thermodynamics. And T is not just temperature of the gas. You have to be very specific. It is the absolute temperature of gas. And the reason why it's the absolute temperature of gas, because you're going to be measuring this in the Kelvin scale. It will have no negative value, it will have only positive values, starting from 0 onwards. And R is the universal gas constant, having this value of 8.31. The units for R are joules per mole per Kelvin, because why is R joules per mole per Kelvin? Because the units for PV become joules. Newton per meter square into meter cube gives you Newton meter. Newton meter is joules. And this side has joules per meter square into joules per mole per Kelvin into moles into Kelvin. So the units of PV are joules, that's why. You can also just say Newton meter if you want. But it's the same unit. 8.31 is the value. So use this relationship and the number of moles is equal to mass over MR to find the MR of substances, or in this case mass. For example, check this question out. The volume of a sample of ammonia is measured at temperature 60 degrees centigrade, which means that this has to be first converted into the Kelvin scale. And the pressure is 103 kilopascals. Now 103 kilopascals should be converted to pascals. And the volume is already given in meter cube, so that's good. And they're saying, what is the mass of the sample of ammonia? So how does one solve this? You want the mass of sample? So what you do is you plug in this into PV equals to nRT, and knowing that N is mass over MR. So you first find N from this relationship, plug it in here, and then find mass. So the pressure was 101 kilopascals, which is 101,000. Volume was how much? 103, sorry. It's 103,000. Volume was 5.37 times 10 power minus 3. Number of moles into 8.31 into temperature would be not 60 degrees but 273 plus 60. You got to convert that into the Kelvin scale. And having done that, you start solving this. And what do you get on the left hand side? Anybody give me this? Come on, come on, come on. Come on, come on, come on. Come on, come on, come on. 553.1. Okay. And then on this side, 333 into 8.31. And you find N then. So what is here? 2800. So what do you get number of moles as? 553.1 divided by 0.197 moles. Then you got to plug this into mass over MR. And the gas is what? Ammonia. So the MR is 17. So then this is 0.197 is equal to mass over 17. You get how much? 3 point? So therefore the answer in this case would be D, 3.4. So I'd like to solve some of the questions on gas laws before going on with. So I want to go over this questions, a couple of questions from this worksheet. The first one being, this is question number 1 on worksheet number 2, page 27 in your notes. A mixture of neon and argon has a mass of 0.275. So this is a mixture who have this mass of gas. The mixture is placed in a gas syringe and a temperature at 25 degrees centigrade and a pressure of 100 kilopascals. Under these conditions, the mixture was found to occupy this volume. And they want to find the average MR of the mixture. When they want to find the average MR of the mixture, it's like them treating the mixture as one gas and finding that gas is MR. So how would I use this relationship to find that? There are two parts to the relationship. One is then I'm going to be using the fact that PV equals to nRT and finding out the number of moles, and then plug in that formula. Number of moles is mass over mR, and having been told the mass was this much and number of moles I'll find from this relationship, plug in and find the mR from here. इसमें से डेटा में क्या दिया हुआ है? The pressure is given as 100 kilopascals. The temperature is 25 degrees centigrade. So what do you do with 25 degrees centigrade? You got to make that into Kelvin. And the volume is 200 cm cube. You got to also convert that into meter cube. And obviously kilopascals will have to be converted to pascals. So how much is pascals? 100 kilopascals means into 1000. Okay? Now then volume is how much? 200 over 10 to the power of 6, which is 6 zeros. I put the 6 zeros because I like to simplify. Then equals to n. R की value is 8.31 from the data booklet. It's given in the data booklet, by the way, first page of the data booklet. And temperature is how much for this? 273 plus 25, which is 298. Then I cancel the zeros out here. I got 5 zeros here, and I've cancelled 5 of them out, and 1 0 here and 1 here. So I'm left with what? 20. And I have this as my R into T. R into 298. Using this, and I can find N. In this case, what do you get N as? Anybody? Sorry? 8.1? Exactly 8.1? 8.08. So 8.08 times 10 power minus 3 is equal to mass is how much? 0.275 over mR. So mR would then come out to what? 30? There you go. 3 significant figures or 1 decimal place for mR, and you have the answer. Now, that part was using PV and RT. Then they're saying using this answer find the percentage of neon. Well, that's a fun bit because it's neon and argon. And if agar एक का mass is, neon का mass कितना होता है? Is it 10? 20. And argon's is 40. And अगर neon की percentage x है, तो argon की होगी 100 minus x. And the average MR would be 20 into x plus 40 into 100 minus x over total percentage, which is in this case 100. And that equals to 34.1. And if this equals to 34.1, and you can solve for x this way. I am assuming x is less than, definitely less than 50, maybe around 30s mein hoga. Somebody has to do the math for me and tell me. So x in this case is 29.5. Is that what you guys are getting? Okay. And you know what? You double check this. If that means approximately what they're saying is on 100 more atoms, 30 are neon and 70 are argon. So take 30 of these and 70 of these and average them by 100, you will get 34.1. That's why we did this. Then it says this part is about intermolecular forces, but since we're already here, neon has a boiling point of this much and argon has more. Name the force that has to be overcome in order to bond neon and argon. Explain what causes it. So what is the force? It is van der Waals due to induced dipoles, and it's the attraction between temporary dipoles in the molecules of neon. It's for 3 marks. Yeah, where the positive attracts delta negative. I don't know what else to write here. For 3 marks. Unless I know exactly what the marking scheme says, but this is the data. It's induced dipoles here, and the dipoles were either temporary or reduced, and the attraction is between the positive and the negative ends. And it says explain why argon has a higher boiling point than neon. Because argon has more electrons in its atoms, therefore stronger van der Waals forces. Okay? I want to look at the next question also, but I can, this has many parts to this, and I can quickly answer them. The last part is requiring PV and RT, but PV and RT comes part of bigger questions, and so let's solve this. In this case, aluminum reacts with chlorine to form a white solid chloride that contains 79.7% of chlorine and sublimes, which means changes straight from solid to gas at only 180 degrees centigrade. For all intents and purposes, this is a low temperature. So if something that sublimes or melts or boils at low temperature, that should tell you it's only one type of substance that does that. Simple molecular structures. And if they are simple molecular structures, what kind of bonding will they have? Bonding will be covalent. Intermolecular forces could be van der Waals or hydrogen bonding, but the question says describe the structure and bonding. So now, what's the structure? It's a simple molecular structure held by or containing covalent bonding. And the sublimation temperature is low. As the van der Waals, because now it's simple molecular, it has van der Waals forces between the molecules are weak. That's the idea. Then it wants to find the empirical formula of this chloride. Uske liye, you have to know that it's aluminum and chlorine, and you certainly have been given ratio of their masses. What is the ratio of masses given? They had told you that it's 79.7% chlorine, which meant that it is only 20.3% aluminum, because total percentage has to be 100. Then you'll want the ratio of their amount or moles of atoms. Ratio by moles. So uske liye, all you do is just divide by the AR. I think it's 27. I'm not sure, 27.1. I forgot. And you divide and then you simplify this ratio. And you would get the simpler ratio as 1:3, which will mean the empirical formula is AlCl3. Then the gas loss part is the third part. Once having done AlCl3, it says here that find the relative MR of this chloride. They've given the temperature, Kelvin में करना है, इसको pascals में करना है, mass दिया हुआ तो MR निकाल सकते हैं, and volume is 200, उसको फिर हमें meter cube में करना है. So what you do is you plug it into PV equals to nRT. Pressure is 100 kilopascals. Volume is 200 over 10 to the power of 6, that's 6 zeros, equals to number of moles is N. 8.31 into temperature, which is 200 plus 273, which is 473. So you solve for N here. Once you solve for N here, which by the way, I don't know what it was, then you plug that into number of moles as mass over MR. And mass was given to you as 1.36, and you solve for MR using M here. These number of moles, plug them in here, solve for MR. And the MR would come out to somewhere close to, it has to, because, that's what it is. It's 267. I know it because I know it, but yeah. And if that's what you get, and the formula of AlCl3 is actually 133.5, and iska mass 267 hai. So that's double the formula, which means the molecular formula is Al2Cl6. And by the way, this is the proof that AlCl3 became Al2Cl6, जो dative bonding में हम करते हैं. So now I want to go to the next part of this chapter and continue the questions that you've been given from the worksheet especially do worksheets 1 and worksheets 2 for this. Let's move on to the next thing. So what I want to talk about now is the fact that if I talk about, I know this much, I know my Boyle's law and I know my ideal gas equation. And Boyle's law said that PV is equal to a constant always. So which meant that if I were to talk about my PV against pressure, the graph should always be a horizontal line, the value should always be constant. And that's what it should be. And in a very small range at room pressure, this was generally true for gases. But when we studied the phenomenon much more in detail, what we realized was that this was not true for any gas at the extremes of pressures and temperatures. What that meant was that no gas was actually having a constant value for PV. So generally the value changed. You already see the value, but some of them change like this. The value, instead of staying constant, would actually decrease or increase. Now, first I'll give you the overall summary and then I'll go to the slides that have the detailed words that I'm going to speak about. Now, the reason why this happens is because what we found out that there's no gas that behaves ideally. So the ideal gas equation is for an ideal gas, but the ideal gas is a fake concept. Just like there is no ideal girlfriend or boyfriend. There is no ideal gas. It's just a myth they all perpetuate. Anyways, so moving on from that lame excuse, or lame joke, analogy. So an ideal gas is supposed to have a constant value for PV, which means an ideal gas is supposed to half in volume if I double the pressure. It's supposed to quarter in volume if I quadruple the pressure. So to make the PV relation constant. But we've found no gas that does that. And the reason is that two major assumptions we've said in our initial theory yesterday were the last points number 5 and 6. Those are not ignorable for real gases. Point number 5, or the major assumption, was that we assume that no gas has any intermolecular force. Or gases have no intermolecular forces. We know that to be false because we know many gases to have hydrogen bonding. We know many gases to have very strong van der Waals. Now that affects this relationship. Second problem that we assume is, we assume that the volume of molecules is negligible compared to the volume of gas. And imagine this analogy that you're sitting in this room. Imagine your cells to be atoms or molecules. Let's say that you guys are molecules. Your body is a molecule. You cannot compress that. But you are scattered in this room. And there's a lot of space between many of you right now. I can get you closer, right? I can get you even closer and closer. Till a time when all of you are stuck together. That becomes the liquid state. Because you can't compress it any further. You might be able to move between each other, slide over each other, but you are a liquid state. And if I were to tighten you to the seat belt you, that is exactly what happens in the solid state. Now let's go back to the gases that you guys are in right now. Now this distance that you have amongst yourselves in this classroom is a much closer distance than, imagine the classes you all go home and you all live all over Karachi. It's a huge city. The distances between, unless you guys are living in the same street, are pretty large between you guys compared to the distances right now. Some of you have much closer distances than others, but that's the attractive forces that we talked about, you see. That's what happens when you have attractive forces. You get closer. But if you had no attractive forces, you would be far out and you will be in random motion, so you'll never really come close. So the ideal gas versus real gas में मसला यही है कि दो चीजें हैं. Real gases have attraction and real gases have volume, like you guys. The gas molecules. What that means is, theoretically speaking, if you're all as clumped together as a liquid state, and if I were to double the pressure of you in the liquid state, would your volume half? It would not even change a bit because liquids are not compressible. But in a gaseous state, like the state you are in right now, if I'm supposed to double the pressure, the volume that you guys occupy should half, which means the volume of the space between you guys, because your volume can't change. But only the volume between your space halves, not the total volume. But initially, we assume that your volume is nothing compared to the room. The empty space is so much more that if that only halves, it's approximately the whole volume is halving. But the problem starts happening when you reduce scale like this. Like if this represents a large room and these circles represent your body's volume compared to the whole room in this case is nothing. So when I double the pressure here, the volume should half, but only the empty space halves. But the empty space is so big. And you might say, well, this doesn't half. And you say, it doesn't matter, this was a small volume. Andaze say, halving the volume of the room will be enough. But imagine you keep doing that to a level where suddenly you half, and suddenly now you get your 4 molecules like this. The same 4 in this much space. And by looking at this space, you can clearly see that the empty space is no longer like thousands of times larger than the actual molecules. They're almost the same. And here, if I were to double the pressure now, only the empty space would half, and not the volume of the molecules. Let's say that this empty space is 1000 ka volume meter cube for some reason. Let's say dm cube. And let's say each molecule is 1/4 of a dm cube. Actually, no. Okay, we can use dm cube because that's a stupid unit, but let's say there is some unit and this is the relationship. Let's say each of these is 1/4. So total volume kitna ho gaya iska? So total volume is 1 whatever unit for the 4 molecules together. And the empty space is 1000. And the total volume is 1001. Now if I double pressure, this cannot half, only this halves. Ye kitna ho jayega? And the total volume is not 500 but 501. But you can say, yaar, 100 because pehle volume tha 1001. But that cannot half because only the empty space halved. But what is the half of this? 500.5. But using this, it is 501. So 500.5, 501 approximately equal है. तो यहाँ मसला नहीं है. मसला जब हो रहा था कि जब इस आते हो कि वॉल्यूम तो 1 है क्या, लेकिन एम्प्टी स्पेस हो गई है अब सिर्फ 3. टोटल वॉल्यूम कितना हो गया? 4. But now if I double the pressure at this state, the empty space is the only thing that will half. तो 3 का क्या हो जाएगा half? 1.5. और टोटल वॉल्यूम कितना हो गया अब? 2.5. So I went from 4 to 2.5 when I was supposed to go to only 2 because half करना था ना. And you keep doing this even more at this stage because now the error is much larger. 4 to 2 से 4 to 2.5 में the error between 2 and 2.5 is quite large. This is how much? 1 in 5. 20% error है ये. 20% error is a pretty large error in physics. 1-2% is okay, percentage errors. 20% is a large error. The point being that as the volumes become smaller, the volume of molecules is no longer negligible. And that's what happens with everybody. Every gas. The other thing is that sometimes, this is one problem, but this happens in very low volumes. This happens when the volumes are really small. Like molecule bahut kareeb. This is when they approach the liquid state. And when is volume really small, when pressures are really high. Second problem is, यहाँ भी होता है. अभी हमने बात की थी ना कि इसका pressure double किया तो volume कितना होना चाहिए? Half होना चाहिए, right? Now some of these molecules are attracting each other. So if you get them closer, by halving the volume, what will happen to the attraction? It would increase. So should they get even closer? Then yes. So instead of them going half, they become closer than half. So that's the opposite problem. Okay, sometimes you can compress them enough, sometimes you compress them too much. And there are two problems. One of them happens because of intermolecular forces, and one of them happens because I can no longer ignore the volume of molecules. All gases have the volume of molecule problems, but what they all differ in is their strength of intermolecular forces. So gases that have weaker intermolecular forces will attract each other less, will be more ideal. That's why this graphic, so to talk about this is what happens. You saw that, if you remember this, I did this earlier. This was when, this part is the decreasing part. Now, why would this decrease? If I double pressure and the volume becomes half, it should remain constant. But if I double pressure and the volume becomes half and the molecules get closer, then they have strong intermolecular forces and they get even closer than half, then this volume will become less than half. So the amount will become lesser. So this dip happens because of intermolecular forces. But slowly and slowly, the other problem becomes more important, which is the fact that I can no longer ignore this. Now, this is a lot of explanation. You do not have to recreate this explanation. What you just need to know is this, that there is something known as negative deviation and positive deviation. Negative deviation happens because of intermolecular forces, and the positive deviation happens because of volume of molecules no longer being negligible. And jitna stronger intermolecular force hoga, utni negative deviation zyada hogi. Which is why in your slide number 14, this is what you have. What I explained to you right now is all in slides 14 and 15 in text form written. This is basically, look and notice this. Which gas is going down the most? Ammonia. It has hydrogen bonding, stronger than van der Waals. HCl is stronger van der Waals than O2, so it's dipping less. You notice two gases don't dip at all. Hydrogen and helium. And the reason why they don't dip is because they have almost non-existent van der Waals. And the reason why they have non-existent van der Waals is that both of them have only 2 electrons. Helium is monatomic, so 2 electrons hote hain. Hydrogen has 1, but there are 2 of them. So both are monatomic gases. They have only 2 electrons in the molecule. So the van der Waals are very, very low. If they're so weak that they have no negative deviation. So your job in the exam is to know that the most deviation comes from the hydrogen strongest intermolecular forces, which means they are the least ideal. And hydrogen and helium are the most ideal. But none of them are really ideal because there's no gases ideal. They're all gases, but the closest to ideal gases are hydrogen and helium. Ye yaad rakhna hai aapne. ठीक है? And the least ideal is one that has the strongest intermolecular force. Now, even between hydrogen and helium, there is one that is more ideal, and it is not helium because helium is a noble gas. It is helium because helium has only 1 atom in a molecule, which is smaller in size than hydrogen having 2 atoms overlapping each other. Even though hydrogen has only 1 electron and 1 proton, the molecule of hydrogen is larger than the molecule of helium because helium is 1 atom in the molecule. Hydrogen has 2 atoms in the molecule. So between these two, this is most ideal. Second most ideal, hydrogen. And then baki sab because of intermolecular forces. So that's what you have to know for the exam. Now, what conditions make it less ideal? When the molecules get closer together. When do the molecules get closer together? When volume decreases. How can volume decrease using PV and RT? If I'm talking about decreasing volume, how can I have less volume? If either the pressure is high or temperature is low. So my unideal conditions are high pressure and low temperature. Which means the best conditions are low pressure and high temperature. Kyun? Because I want large volumes. Jitna large volume होगा उसका 2 फायदे होंगे. Empty space बहुत ज़्यादा होगी तो molecules are very far apart and their errors will be negligible. Second, when they're very far apart, intermolecular forces will be weaker. So I want the volume to be, for ideally, I want volume to be high. But I don't control volume. How do I get high volume? What conditions give me high volume? Less pressure and high temperature. So ideal conditions are low pressure and high temperature. Now all of what I just said is in the notes in the slide. So let's go over that to repeat. We have found that none of the gases behave ideally. We have found that the two types of deviation were seen. All show a minimum and then increase. Hydrogen and helium never show a minimum because they only have a positive deviation. Like this. And then the hypothetical gas is called the ideal gas. It's a perfect gas. Again, the term hypothetical because it doesn't exist. All known gases are referred to as real gases. Ideal gases are supposed to obey the law of PV-nRT. Real gases will not exactly obey the law. They are inaccurate. You want ideal conditions for them to obey the law, and we just discussed the ideal conditions, which are low pressure and high temperature. Because you want volume to be high. So you want volume to be high by temperature being high and pressure being low. And why don't the real gases behave ideally? Because they have attraction and we cannot ignore the volume of molecules. And these differences are especially noticeable at very high pressures and low temperatures. Very high pressure and low temperatures means molecules are closer to each other and their volume is not negligible and the van der Waals are stronger. Okay? So, what I just explained to you, why does it decrease? The molecules attract each other, they get closer, and in hydrogen and helium, there are no intermolecular forces are very small. So that's why they don't have a minimum. So the real way the two assumptions become really true is when the volume tends to infinity, meaning volume becomes very large. When the volume becomes very large is when the pressures are decreasing and temperatures are increasing. Those are what we call ideal conditions for us. So when we do the measurement, steam engine for that matter, or factories, we already have high pressure, temperature, so great. And if we keep the pressure, room pressure is fine. That's low pressure and high temperature, which is why in the real world, the math works out to be approximately correct, so we're okay with this. So the law is obeyed at low pressures and high temperatures, which means it is not obeyed at or bad at the opposite end. And then you'll have to be given questions like, what kind of gases are least ideal? The one that has the strongest intermolecular force. If you have all these van der Waals gases, then the strongest intermolecular force is the guy that has the most electrons. In this case, that would be carbon dioxide. So this will be least ideal. And most would be hydrogen and helium. But even between hydrogen and helium, you would say helium. And that's the kind of questions you'll have to answer. The answering of the questions is actually much easier than what I just explained to you. But you will not have to recreate the explanation. All you have to know is that which gases have the most deviation, the conditions that are needed for ideal situation, which is low pressure, high temperature, and the two assumptions that we get wrong. That are the reason why we have these problems. The assumptions are that volume of molecules is negligible. We know that's not true, but we assume that it's negligible. And second assumption is we assume there are no intermolecular forces, no attractive force between molecules, while we know that they are. So having learned this, try the questions in this worksheet. It should not be a problem for you to do the questions now. All right? I'll see you guys tomorrow.